special information coming. So please go ahead.
So, yeah, thank you very much. So I'm happy to talk about this. So this is indeed work. Why this doesn't work now? Now it works. So this is work which I have done together with Anton Sokolov. It was, in fact, it was initiated, this kind of investigation. They were initiated by my previous PhD student, Anton Sokolov. And you realize, I mean, he comes after me in the alphabet, but I have chosen to really to emphasize that he was he really initiated this program, which we are now investigating, by giving him the possibility to stand in name before me. So as we all know, so there are many experiments hunting for the axions, and here are the logos of some of them. Of course, my beloved ALPS-2 light shine through wall experiment, which will start data taking in the next 2 weeks or so. Then there's CAST, Abracadabra, Haystack. You see, the people they give very nice names to their experiments, and so it's flourishing field. And most of these experiments, or all of them which I have listed here, are based on searching for the coupling to the photon, which is of this form. So it's proportional to FF tilde, or in the field strength, in the electric and magnetic fields, it's an E dot B interaction. And so these are experiments like ALPS is searching for light shining through a wall. CAST is an helioscope. And the others which I've listed here, Abracadabra, Haystack, or the CUP experiments in the Center of Axion and Precision Physics, or ADMX, they are helioscopes. They look for somehow light shining through from the cosmos inside a cavity or other devices. Now. Always takes a bit, I don't know why this takes so long. So the aim of the next generation of such experiments is to reach the band of photon couplings predicted by vanilla Axion models, like the KSVZ or Axion model, which is parametrically given by this formula. So it's a linear function of the Axion mass. And there is some model-dependent factor, this E over N from the electromagnetic and the color anomaly, and there's a factor then which takes into account the mixing with the pion, as we heard in the first lectures by Giovanni Villadoro in the training week. Now, and so these you see these kinds of experiments which we are talking about. They are searching for this. So and mainly haloscopes. They really try to dig deep into this prediction. Now, what I want to report here is, maybe this is I have always pressed twice or 3 times. Was this before? A feature observed before? I don't know. Okay. So I will report here on the construction of variants of this KSVZ model with enhanced electromagnetic couplings, which can be probed very soon, for example, by ALPS-2 or by JAXO and so on. And this is based on this work with Anton Sokolov, which I was talking about before. So I just, as a recap, I just start with the normal KSVZ Axion model, which I have also introduced or talked about in the training week. So what was done in this KSVZ Axion model? One added to the standard model a singlet complex scalar field, which features a broken global U1 Paget-Quinn symmetry and a vector-like fermions in the fundamental of color singlet under SO2 left and neutral under hypercharge. And I've always to press 3 times and then it works. Assuming that under this U1 Paget-Quinn, the fields transform in this way, so to say the complex scalar field has a Paget-Quinn charge 1, and the left-handed quark has a Paget-Quinn charge 1/2, and the right-handed has -1/2. Then you can easily convince yourself that the most general renormalizable Lagrangian can be written in this form. So this is the Mexican head potential for the scalar field, which leads to spontaneous symmetry breaking. This is the normal cage kinetic term involving the SO3 covariant derivative for the quarks, and this is the most general Yukawa coupling, which you can write down, which is symmetric or which is invariant under this Paget-Quinn symmetry. And then, as we have seen, then of course, when you decompose the scalar field in polar coordinates, then you see that this model features 3 BSM particles. One, the excitation of the Goldstone field, which is massless at the tree level. So this is this angular field. Excitation of the radial field with the mass proportional to the symmetry breaking scale. And a new fermion also with the mass proportional to the symmetry breaking scale. And if this is very high, you just integrate out this new fermion. Now I have to press even 4 times. Okay. And then for large breaking scale, the latter two are heavy and may be integrated out if one is only interested now in the low energy effective field theory. So now, when you now integrate out this scalar, the Axion, then you remain with this effective theory for this Axion field, or for this pseudo Goldstone boson, or which will be now it's still a Goldstone boson. But you have this unconventional quark mass term if you just put in this radial decomposition. And now this last term can be brought to the standard form of a standard mass term by performing the field-dependent axial transformation, which with this axial transformation, this term is so this phase is removed. And however, one has to take into account that the fermionic measure in the path integral is not invariant under such space-time dependent axial transformations. In fact, it's so bad. Can I push a bottom here? That is, maybe it's better like that. So, okay, they'll do it like that. So the fermionic path integral is not invariant under space-time dependent axial transformations. And as Fujikawa has given a nice derivation using the gauge invariant heat kernel expression for this for the determinantal change of this measure. And the result is, as we all appreciate and love, is that you get essentially the anomaly from this calculation. So, and in a sense, and this means if you then insert this into the into the Lagrange before. You did this space-time dependent field transformation. Of course, from that, you will get from the kinetic term also such a term, which, however, if you integrate out the quarks, do not contribute at low energies due to the Feldman-Sutherland theorem. And then at the end, you are, if you integrate out, you are left just with this term. And so at low energies, maybe it works here when I'm standing here. So could be, maybe it was too far away here. So I mean, but I can also push. Thank you. So you can safely out the heavy exotic quark, and then you end up with this nice formula, which means that that theta equal E over V over the vacuum expectation value in this theory is a dynamical theta parameter, and then the story goes that the strong CP problem is solved by this because the theta bar can be absorbed by this field, and the effective potential of this field, of this Axion field, has a zero at vanishing expectation value. Now here it works. So I stay just here. So thanks. So now allowing for electric charge of the exotic charge of the exotic quark that is charged under U1 electromagnetic, the generalized case with Z Axion can be described by this formula. We have seen this also before in my lecture. Now it doesn't work again, but then I do it here. So the Axion decay constant in my normalization here is given by V sigma over 2n. So in order that here there is no n from the anomaly factor is appearing. And here are the anomaly coefficients for this kind of for this model. You can read off here. So n is equal to 1/2 in my normalization, and the n for the electromagnetic fields is the 3 for the 3 colors in the fundamental representation times the charge itself, the electric charge itself of the quark to the squared. Now, and then the story is, of course, it's just standard. You can integrate also out the gluons, or you can below the QCD scale, you can match to the chiral theory, chiral Lagrangian, and the mixing with the pion. From that, you get the Axion mass in this form, or more correctly or exactly by this formula, and you can get the Wilson coefficient for the electromagnetic coupling, the Ca gamma, which has this model-dependent factor E over n, and this factor from the mixing with the pion, and this has been also been calculated with a nice error bar or more precise by Guidi di Cortona and Giovanni and Ed, and so all in the audience. Now, so as I mentioned from the beginning, there's this band of predictions for the electromagnetic coupling. There have been also nice works by Luca Di Lucio, by Mejia and Enrico about a definition or what are the preferred ranges for E over n in case VZ-like models. But as you notice, this is still, so for example, ALPS, my beloved ALPS experiment is measuring in this region. So I would have liked, of course, to have a model which predicts something, an Axion model, which predicts something here instead of here. So, and then, but I didn't order it for my PhD student, Anton Sokolov. He came alone for me and told me, what if this exotic quark as a particle, if it carries a magnetic charge? What happens if it carries a magnetic charge? And then we first, clearly its existence, then this exotic quark would not be only motivated as an ad hoc particle which one introduces or adds to the standard model in order to solve the strong CP problem, but at the same time, its existence would then also explain charge quantization, because as soon as you introduce a monopole, then by quantum consistency, at the end you have to, the electric charge has to be quantized. And a magnetically charged fermion or quark is a monopole, so to say. Yeah. It's not one extended monopole, but it would then be a fundamental monopole. And then, of course, then just by power counting, so to say, I would say the expected induced electromagnetic coupling of this guy should involve the magnetic charge squared instead of the electric charge squared. And the relevant factor in this coupling should be alpha magnetic rather alpha electromagnetic. And now, clearly, of course, this coupling would be parametrically enhanced due to charge quantization, because alpha magnetic would be the fundamental charge, or the fundamental magnetic charge squared over 4 pi, but the fundamental magnetic charge, because of charge quantization, should be 1 over the unit of electric charge. And then just from this, you would infer that alpha magnetic is proportional to alpha electromagnetic to the -1, or which leads then to the fact that GAMM over GA gamma gamma should be of the order of alpha to the -2. So it should be, there should be an enhancement of 10 to the 4. And then you suddenly, you see, you make for this simple KSVZ prediction, you would say, okay, whoop, this shoots up by this factor, and there's no, in principle, so if you take the minimal possible magnetic charge, then this is the jump which you would get just for the KSVZ axion without playing further numbers in this M. So, and then suddenly a QCD axion which comes from this generalized KSVZ axion model would be suddenly observable by ALPS 2. And so this made me, of course, then I said, okay, this is very interesting. So let us look into this more in detail. Now, so here's now it comes. So what if the exotic quark in KSVZ model indeed carries also a magnetic charge, or carries a magnetic, or just a magnetic charge? It doesn't matter. So what I want to do is to integrate a heavy magnetically charged quark, so like before. But then to do this, we have to start from an extension of the quantum field theory of electric charged particles to the quantum field theory of electric and magnetically charged particles, so-called quantum electromagnetodynamics. And this is not so easy. So first of all, I mean, there are not many candidates for this series, so there have been some investigations before the advent that when gauge series, non-abelian gauge series were really hyped. So shortly before, you say in the 70s, Schwinger and Zwanziger, they were thinking about this question. And Schwinger, he developed a quantum field theory for electric magnetic charges starting from the operator representation and Dirac quantization of the theory and so on. But however, the arguably best fitted formulation of the QMB has been developed by Zwanziger. So it's very much suited for our purposes because it starts with a local Lagrangian in terms of two gauge potentials, which allows, because it's a local Lagrangian, it allows the application of the standard apparatus of local quantum field theory to tackle problems in this model. And it has, of course, the drawback is, but this was one of the drawbacks is just that manifest Lorentz invariance in this theory is lost because this local Lagrangian depends on a preferred direction. So somehow one has to live with to introduce somehow the concept of a non-dynamical string, so to say, like from the beginning with the investigations of Dirac. And however, because I said, because this formulation allows the application of the standard apparatus of local quantum field theory, in particular also the introduction of path integrals to write the generating functional of Green's functions in terms of path integral. All this can be applied, and then with this apparatus, it was possible by Brandt, Neri, and Zwanziger 7 years later. Then after the introduction, one could show that physical observables, or here in this case, gauge invariant Green's function of current operators, that they are Lorentz invariant, provided that the charge quantization condition is satisfied. So, okay, so let us just sketch how this was done by Zwanziger. So the problem is of course with so now if you want to introduce path integral or the quantum field theory, you want to formulate the gauge theory in terms of potentials. However, with just one gauge potential, you cannot satisfy both Maxwell equations. The one, so the normal d mu f mu equal to the electric charge, to the electric current. The other one, where now I have switched the notations. I'm not putting tildes. So if there is a d, then it's the dual. So because it would get too cumbersome in the expressions to put tildes over expressions. So this is the dual of the field strengths, and this should be equal. This d mu of this dual field strength should be equal to the magnetic current. However, if you have just one gauge potential, then this one is automatically zero. Then you cannot have write this in terms with one gauge field. So, but Zwanziger has observed, or I think maybe also other people before, that the general solution of this equation can be expressed in terms of two gauge fields, A mu and C mu, where F is essentially the wedge product between D and A, where this wedge product is just the usual in components. It's A mu B nu minus A nu B nu. So this is the normal expression for the U1 gauge field, and this FD is D wedge D. However, it's so to say corrected by these factors, which are special solutions of these equations, which involve an arbitrary fixed 4 vector and this integral operator nd to the minus 1, which satisfies which is just the inverse of n times d as an integral operator. So and now, so one can just by inserting this expression here, one can see that this is nicely solved. So but you had to do it by the introduction of these string-like corrections to these gauge fields, or to the expression for the field strengths. So the gauge field these gauge fields, of course, depend on the choice of this 4-vector n, the choice of the representation of this integral operator, and the choice of gauge. Now you can exploit some identities in order to write the field strengths and its dual locally in terms of the potentials alone. So you can write them in this manner in terms of the potentials alone. So there is no current involved anymore. And now if you now insert these expressions into Maxwell's equations, or in this generalized Maxwell equations which we had before, then you get these complicated expressions. But it's clear from this construction to any solution F of Maxwell equations, there exists potential A and C related locally to F by this relation, and which satisfy these equations. And conversely, of course, every pair of potential which satisfies these two equations, they define a unique solution of F of the Maxwell equation. And of course, A and C are highly non-unique, so the one has so this is a much bigger space one has of functions. Now, and Zwanziger has now searched for the Lagrangian, for the local Lagrangian, whose Euler-Lagrange equation coincide with this equation. And this is the Euler-Lagrange equations. So it involves this d wedge A, the d wedge C, D, always cross products, and here are two terms which are which just n times d wedge A squared. And one can check, so one it's a bit cumbersome, but you can check that if you do now the Euler-Lagrange equations for this system, then you end up with these generalized Maxwell equations. And before we have seen that then there exists F and A which satisfy the generalized Maxwell equations. So far, so good. Now, and so at least classically, one gets the normal Maxwell equations, and there is no independence from the point of Maxwell equations. But now, what about the equations for the currents? Yeah. Yeah.
By saying we need to break the Bianchi identity because, of course, that requires this other.
Yeah.
GI is the Oxford parameter. You must have a small parameter, something because we didn't see these. I mean, we know that the Maxwell Lagrangians, as they are the Maxwell equations.
No, at the moment, this is what these are were Maxwell Lagrangians in the background of a conserved current. So there is no coupling constant. The coupling constant will only arise then. So I mean, this was the free Maxwell field you can express in many things. Now the question is whether also the field equations for the matter will be okay. So and the matter has the coupling. And here now I start. So, and I think this is also very important. I mean, you still just do now relativistic classical dynamics of electrically and magnetically charged point particles. So realize the electric and magnetic currents by point particles with trajectories xi of tau I, where tau I is so to say is essentially the time parameter for this. Yeah.
Yeah, in the Lorentz violation we were talking about, that is potentially coming into this via the streamline.
Via this n, yeah. So, and here, and now we are just considering now the electrodynamics, so to say, of classical point particles. So you would realize the currents like that. And then you can derive the classical equations of motion plus the equations of motion of the gauge potentials from the requirement that the total action, where this is this Zwanziger action, this is the action of the point particle, so to say, is m times v is the kinetic term, so to say, of the point particle, and Si is now the interaction of this current with the gauge fields, and so of course this EI. So and here are now the couplings. Here are the coupling constants, which I said. Here is the EI and the GI so EI couples the electrical charges, they couple to the A, and the magnetic particles couple to the gauge field C. And now if you derive now the equation of motion, of course the equation of motion for the Maxwell field will be completely fine. There will be no dependence on n. However, if you now consider the equations of motion which you get from the variation from minimizing the particle trajectories, you get this equation, and the Lorentz force. You see the Lorentz force is now in terms of this d wedge A and a d wedge C. And d wedge A is something like FD, and this is something like F. However, or F and FD if you insert the expressions before. However, there is a correction factor which depends on n now. And now you could say, oh, okay, I mean the Maxwell equations are okay, but here is a correction, and this correction is so to say multiplied by these factors of the electric and magnetic charges of the particles, and so you get the familiar local term plus an interparticle interaction at a distance depending on this inverse operator. Now, but the crucial observation made then by Zwanziger is that this last term, which seems to spoil the Lorentz invariance, because the Lorentz invariant result would have been this, which you would have done. This seems to spoil the Lorentz invariance, but fortunately it does not contribute to the dynamics in the following sense. If you represent you take now represent the kernel, for example, in this kind of form, then you find that the support of this kernel, which is now in this integral, is restricted to the string n mu s, so to say. So the distance between the particle I trajectory and the particle J, so they should so to say should be of this size. But this condition can only be satisfied along exceptional trajectories, because there are 4 equations, but only 3 parameters for this. So only at very special things you are really both are meeting, so to say, in the string. And this is the reason why this essentially, so classically this does not contribute to the dynamics. You can just require by continuity on classical mechanics that this fits. So, okay, now we come to the quantum field theory. Now, the quantum field theory, quantum electromagnetic dynamics, as defined by Zwanziger, is what you would have guessed, is just now this Zwanziger Lagrangian, yeah. No, I mean this is only in this equation. No, before I have two. You see this is the equation you can get, but what I used here is F is essentially D wedge dA up to this correction which involves the magnetic current. And F dual is this D wedge D, but it involves the electric current. Yeah. And here at this point, yeah, I mean you have to integrate over both fields. You have two. In principle, here, in a sense, you could also classically you could understand it in the following way: that these two equations they are two equations first order in time, and therefore you reduce the numbers of degrees of freedom from two gauge bosons, so to say, or two photons, so to say. There is only one photon. You cannot see it so direct. I mean, you have to do the calculations. I mean, yeah. But they are completely. They are so mixed. So I mean, so this. Huh? If you have to add a gauge fixing, and then in a sense, if you do the gauge fixing, but here so just to say it, so here the step from here to here is just you insert. Yeah, I mean this is trivial that you get from the variation of this. You get these terms, and then you insert here this expression from above, and there are also these currents, and then you get, so to say, from this you get this interaction. Yeah. I mean, this was easily. I didn't put it here, but this is easily seen if you do the canonical quantization, so to say, and then you even on the classical level, so you see that. Yeah. No, there is no extra constraint. You don't need an extra constraint. Yeah. No, this here is you see what was before. So what I wanted to say, I have to do it like that. So you see here curl of C is FD minus this.
Okay, but the next line in notations say that F of below. Okay, F of D is epsilon mu kappa lambda F kappa lambda over 2.
Yeah.
So,
this is true. This is true. I mean, it's all.
Which relation are you using in page 51?
Here I have used. here I have used the relation I have inserted for this. I have used this one, this one for the D wedge C and this one for the D wedge A.
You are not using this
No, I don't know. I'm not using this. I don't use it. I don't use it. I just wanted to, maybe I should write it here in X. So it's so to say just to explain what is the dual, what means dual.
It seems that you have two gauges, two independent gauge constraints.
Yeah. But if you do so either the canonical quantization of this theory with this Lagrangian a la Dirac, or you do the path integral quantization of this theory, then you get only one photon and these charged particles. Yeah, I'm failing now to give a easy explanation. That's true. So I should sit down and find this now. But so at the moment we have to. So I mean, Schwinger was sure, and so I think it works, but I have no easy explanation now. So, but at the moment, so if we go now to quantum electromagnetodynamics, I have this 20er Lagrangian, which gives the Maxwell equations. Then I do a gauge fixing by this, so that n dot A and n dot C are essentially free fields, and this is maybe this is crucial. Then this that you have to see how that this works. That this describes only one, and these fermions are minimally coupled, like so. It looks really like a U1 electric cross U1 magnetic gauge theory. But it's through this vector n. It's somehow they are tied together. These fields, and now I've here said that it has to be shown by path integral techniques. This time-ordered Green's function of gauge invariant local operators that they are independent of n mu. If this Dirac-20er Schatz quantization condition holds, maybe, so I just go to the very end and I return to what I said. So the idea, just to give a sketch how this works, or why this is Lorentz invariant, is the following. For the proof of this independence of Lorentz invariance of the point particle theory, which was showing before, it was essential to use the point structure of the particle charge, because by that you could see that only for exceptional trajectories there was an independence at all, and otherwise you got the normal electromagnetic dynamics equations from this formalism. Now, and now the idea of Brandner and 20er was that the quantum field that you write, so their proof was based on the functional integral formulation of QEMD. So here it's really, so you are really now integrating over all gauge fields, all both over this A and C, and then over the fermion fields. And now the functional integral over the fermions, as we all know, or that's not all, but as many of us probably know, can be converted into a series of integrals over closed point particle trajectories. So this is the word line representation of the path integral of the fermionic path integral by Feynman and by Schwinger. And then the remaining Gaussian integration over the gauge fields can also be performed, so everything is quadratic. So formally one gets the expression in terms of in terms of currents. And now the n-dependent term in the effective action functional of this theory is proportional to this Eg minus Eg and the number of times the trajectory in this of these point particles of one of the particle intersects some oriented and mu-dependent free surface associated to the trajectory of another particle. And this is simply a topological integer, but for some exceptional trajectories, this is not an integer, but those exceptional trajectories are the same as we were seeing before. They form a measure zero subset and can therefore be omitted in the integral over all trajectories. And then if you now require that the set quantization condition that that this difference is 2 pi m for all possible ij pairs ensures that the n-dependent contribution to the action is always equal to 2 pi k. And this ensures that this generating functional is independent of n. So this is somehow so it's important that this Zwanziger formalism works for point particle theories, and then you can take it, so to say, if you express the path integral in terms of an integral over point particles, you can show this independence. So, and we are now, so in a sense, we are relying on this, on this formulation, and go now back, so to say, on our model. So to say, we said, okay, we have the KSVZ Axion model. We have now integrated out the Axion, and we are remaining with this equation. Or with this effective Lagrangian, with this term, and now in d mu, we think we have not only the SO3 color for the exotic quark, which gives rise essentially by Fujikawa then to the Chi-Chi dual, but we have also the covariant derivative with respect to this A and C gauge fields. Now, again, we could show in this paper, if we do this transformation, we could show with heat kernel techniques, we could calculate this LF, or the contribution now from the magnetically charged fermions, and it has this form, which is not very unexpected. So it has this d wedge E, d wedge ED, d wedge C, d wedge CVD, dA, dCd, which is essentially here, this is the electric coupling, this is the magnetic coupling, and this is an electric magnetic coupling. And there are three anomaly factors. So there's this in front of this. It's 3 times the charge squared, the electric charge squared. Here is 3 times the magnetic charge squared, and here is 3 times the magnetic times the electric charge. And of course, then if we have factored out the units of the charges. So here's an alpha. Here's an alpha magnetic, and here's the square root of alpha times alpha magnetic. So this is in a sense, these are the new contributions, so to say, this will give rise to new contributions to the Maxwell equations, these terms, and so there are new terms in the Axion Maxwell equations. So before if the axion has only an electric charge, if this chi-Z axion has no electric charge, or it has a it has only an electric charge, then we get always a contribution of G of the form GAEE, and all these other terms with a GAEM and GAMM, they are absent. So the Sikiwi's Axion-Maxwell equations differ from these equations just by this term 0, this term 0, this term 0. So this is 0 on the right-hand side. Here, both terms. So this is all this divergent. This is also 0, and this is non-zero. And here is so to say the Klein-Gordon equation for the axion. So in the normal axion, in the normal Sikiwi case, you have only the GAEE and no GAMM and no GAEM. So these the Axion-Maxwell. So there are new terms in the generalized Axion-Maxwell equations. Just if you assume that this, so the phenomenology might completely change. Yeah.
So until in the slide, you have used A and C.
Yeah.
And now suddenly we have a single.
Yeah, because I say so. I mean, you can always show that these extra contributions on the classical level, they can be neglected, so to say. These.
Until the slide, it seems that you have been using two vector potentials, A and C.
Yeah.
It comes up with just a single vector potential.
Yeah.
So how do we eliminate function C at this stage? Look at the Maxwell equation in terms of all A field.
Here are always these terms. If you insert now these expressions before, so on the so
You should give us some relation between C and A.
yeah.
In order to write your final equation just in terms of the electromagnetic field of A field. But I don't see any so far.
Yeah. I should provide them. I mean, they are in our paper. So, but these are in our papers.
Because constantly,
Yeah.
suppose that you have dark photon.
Yeah.
To the conversion photon, then this is certainly what you do. You have some charge particle, charge on the electron charge, and also charge also on the W and this is what you usually get generically.
Yeah.
Action coupling for the photon, action coupling the dark photon, and action coupling to photon and dark photon.
Yeah.
But eventually you have just action coupling to ordinary photons.
Yeah.
That means that your dark photon is not an independent field, but some sort of dual of the ordinary photon. But
Yeah, I'm missing. So we have to. We have to after the seminar. Maybe we should look into. I try to explain that. So at the moment you have to believe. So yeah, I thought so. Otherwise, I'm not coming to some of the phenomena. I don't want to talk much about phenomenology, but because this should be done by Anton, but maybe Anton can also give even more explanation of these things. So as I said, there are these electromagnetic couplings, and there's a huge hierarchy because of the DSZ charge quantization condition. So between alpha and this alpha m, and so let us take as now granted that these equations are fine, and I still have to convince you that the last step was legitimate. Now, if these equations are like they are, then the conversion of relativistic axions into photons and back in transverse magnetic fields and solar axion emission through Primakov effect or photon coalescence and so on. They are all given by the conventional suppressions just by replacing the GA gamma with the GA MM. So that would mean, so to say, that these limits, they are all fine, but these are also limits on this GAMM. So it would mean that this axion, if it really has this monopole Philic axion model, this axion would solve the strong CP problem and simultaneously may explain astrophysical hints like the horizontal branch star hint or the TeV transparency hint. Then you can put already from constraint, you could put an upper bound on the axion mass in this model, and this would be of the order of 10 to the minus 6 electron volt. And you see also from this plot that ALPS2 and baby YAXO or YAXO can probe this axion down to a mass of 10 to the minus 7 electron volts. So in this range, mass range, it can be even probed by ALPS2 and baby YAXO. And I'm looking very forward to that because ALPS2 is just starting to take data. Now, in this model, of course, you can, because this fermion, if this exotic quark, if it is produced in the early universe, this can make a problem, make an overdensity. So it's only valid. So this model can only be valid if you have a pre-inflationary scenario. So a post-inflationary scenario doesn't work because then we would have a monopole problem in a sense. So and therefore the axion dark matter, the amount of axion dark matter would be given by the of order the full dark matter in the universe for MA of the order of 6 microelectron volt if the initial angle is of order unity. So this means also exactly in this region, which is also preferred by these astrophysical hints and so on, and also by this coupling, it's quite a preferred region for dark matter. And now, unfortunately, so the low mass haloscopes, which would be good below 10 to the minus 6 electron volt, which exploit solenoidal DC magnetic field and lumped element LC sequence structures such as ADM SLIC or WISP LC in Hamburg are originally designed to search for axion dark matter induced oscillating magnetic field rather than for the induced electric field, which means that they are sensitive only to the subdominant coupling GAEE. And now with a simple change from a toroid, so they normally have a toroidal pickup loop because the coupling GAMM will lead to a solenoidal to a oscillating magnetic field in this direction. Here you get a magnetic field. You get so you should just use this. You just exchange the toroidal pickup loop to a solenoidal one, and then you can access this coupling GAEM, which was pointed out by these authors. And to access the most dominant coupling GAMM, this DC solenoidal magnet in those experiments has to be replaced by a high field capacitor. So you replace this by something like a capacitor which has a strong electric field. And so in principle, so here are the predictions for this GAMM. Sorry, they took another notation. So here's GABB. This is just GAMM. This would be the prediction of GAMM. This would be the prediction of GAAB. And with a experiment like WISP-LC in Hamburg, one could with this solenoidal pickup loop, one could test this red thing and nearly up to the GAB, and with a quite strong capacitor with millivolt per meter, you could test also this GABB, which is this red line or black line. So just to come to the conclusion, we propose a new family of KSVZ type Axion models where the exotic quark carries magnetic charge. These models have parametrically enhanced electromagnetic couplings and can explain various hints with one stroke. For masses above 10 to the minus 7 electron volt can be probed decisively by ALPS-2 and baby AXO, and lumped element search based have to be redesigned to look for that. And Anton Sokolov will provide more details on the phenomenology and maybe also on the theory of this monopolophilic axion later in this workshop. So thank you. And and I see there are quite some open. Yeah?
I understand that you are considering masses which are the usual small masses so that the lifetime is very long, but you have an enhancement in the decay rate of the axion. Does it has any consequence? Because you decay to 100 times larger couplings, right?
No, but still, then you have to. I mean, we are not supposing, so the lifetime constraints, so they would also go, so to say, this is the largest coupling, but the lifetime constraints, they are somewhere here.
Okay.
Yeah?
I have two main questions. The first one is, where did these monopoles come from?
I have, this is, here it was just, this is like, we have no explanation for, the KSVZ have also no explanation for the introduction of this exotic quark. And I just said, let's introduce a magnetic charge to this in addition, why not? And then
There is any connection to this topological effect?
so it could be, so there have been arguments or also derivations that the Zwanziger theory is the effective field theory of a monopole. Yeah.
The second question is, do you have any issues with perturbativity? Now
You have issues with perturbativity, of course. I mean, but the thing is, so the argument is, so to say, that the anomaly is exact to all orders, and therefore, I mean, we have just taken this, so we have two different derivations of this extra thing. So one is with this Fujikawa heat kernel, and the other one was really a direct calculation using the path integral and then this point, using directly the path integral. But for this we had to use again also this point particle representation, but we could do it also exactly for constant fields, which is also the fine limit if you go to low energy effective field theory, so to say. But there have been attempts, but this has not been realized now, but I think this should be done. I think this can be done. We want to calculate, so without assuming any axion, just to calculate the dimension 5 operators in this model and look so to say, what are the changes to the Euler-Heisenberg Lagrangians from the integrating outer monopole. However, this cannot be done on perturbation theory. There must be an exact this must be because in every order and in finite order there will be a Lorentz invariance violation and so on. So it's not. So I think, but if you do it directly with so essentially with Schwinger's methods for constant fields, I think this can be done, and that would be also interesting. However, I would not expect that one would get then, for example, by looking for birefringence, Markov-magnetic birefringence or something like that, when you are testing for the Euler-Heisenberg, that you will be sensitive. There will be this alpha magnetic in the numerator, but in the denominator will be the force power of this, of the magnetic, of the mass of this monopole. And so it's not enough enhancement, I think, that you will be sensitive then to a scale of, maybe you could be sensitive to a TV scale, but not to 10 to the 10 or something like that. But I think it would be worthwhile to follow that. And so this is also one of our attempts, yeah?
So the fact that there's only one line, is that due to the, one monoline, is that due to the charge quantization condition, basically?
No, here this line is now, this is now only for one charge, so to say. So I mean, we have fixed, for example, e to one value and took so this, or this m to one value. So it's 3q squared. So then you can give q squared a large number. So there is no. In principle, this has also a range.
Since you said in the last slide said that you introduced the family of models, so have you thought about? Would this also work with multiple than you thought, like fermions, or do you introduce more multiple? Like
I think you can have larger n, or
would it sort of ruin your quantization?
No, I don't think so. I don't see it. The thing is, no. But and of course you could also say, I mean, this is, we do not have to solve the strong CP problem, and then we are not on this line, but you can do this for any ALP. Yeah, if it has no coupling to the gluons, then this would be also for any ALP. So, but I like to have something which.
We know now, we're confident that U1 electromagnetic is coming from SU2 cross U1 breaking. Can these, this electromagnetic monopoles can be embedded in SU2 cross U1?
I didn't try it, but I don't think that this is a problem. Yeah.
So looking at this plot, as you say, the blue bar, so it's the minimal enhancement that you can have because you put the charge to one.
Maybe took the minimal charge, so to say, the minimal value which you can have for the magnetic charge, and then, yeah.
So that will go just up the line and moving the coupling.
Yeah.
But looking at this plot here, in the constraints, the supernova is the only constraint, but we have also many others, like magnetic work.
Yeah, they can also there. They would also exclude some part here, but I'm not so sure how reliable they are. So I think because we switch on ALPS now, and then you can forget part of these limits, because then ALPS will be on top of all these things. You don't see the others anymore. Yeah. It could be that you if I take, for example, this pulsar limit from my other PhD student, who was also a very good student, Christoph Weniger, he has already excluded this in a sense, yeah. but I don't believe this limit so strong, because you have to believe very much on the knowledge of the magnetic fields, and so I think this depends quite strongly on the assumed magnetic field, how it looks like, and so on. I don't like to, of course, I'm always puzzled, what I should put on such a, what limits, put all the limits. One has to be fair, okay, then I could say, okay, so this was the version from before this, and then you have to put it on. So no, fair. Okay. So thank you. Yeah.